Okay, so let me just go back here to what we were talking about. So we were talking, and actually I'm going to actually do the recording right from here. So section 2.4, as you know, deals with continuous functions. And a function's continuous at a point. Intuitively, a function's continuous at a point if when you trace the function, okay, on your paper, you don't have to lift the pencil up at that point. Okay, if you are tracing a function and you lift your pencil up, then the function's not continuous at that point. That's how I think of continuity. And what we did, of course, was these were example 2. We looked at A, B, C, and D, okay, and we talked about, well, I mean, we know that in A, the function's not defined at x equals 2. So the function's discontinuous at x equals 2. In B, the function's not defined at x equals, I want to be careful. You'll look at the graph of B and you'll see the function has a discontinuity at x equals 0. For C, that function there is defined for all x values, but when you take the limit of the function, as they do here, okay, in, hold on. When you take the limit of the function as x approaches 2 and do the factoring, you're going to get 3. But 3 is not equal to 1. F of 2 equals 1 for this function in part C of example 2. F of 2 equals 1, but the limit as x approaches 2 of the function equals 3. And so therefore the limit as x approaches 2 of the function is not equal to the value of the function at x equals 2. So it's not continuous at 2. And what they've done is they've drawn pictures, and I'll let you look at the greatest integer function. That's D there. You can look at that on your own. But they've drawn pictures of the functions for A, B, and C here. And you can see that the continuities for A, B, and C are each a little bit different. So for A and B, they call the type of continuity at A, for functions A and C, I should say, for functions A and C, the type of continuity is called a removable continuity, because it's easy to fix it. All you have to do for A is just define f of 2 equals 3. And then you know, if you had like in addition to this function here, if this were, well, let me go to part C. It's a little easier. For part C, the continuity at x equals 2 is removable because it's easily remedied. All you have to do is, when x is equal to 2, change your value, change the 1, and make it a 3. Hence, it's called what's called a removable discontinuity. Okay? But in B, you have a different type of continuity. That's called an infinite discontinuity, because the function 1 over x squared, okay, it's not easily fixed. Well, it's not fixable. You have an asymptote at x equals 0. Well, I want to be careful. The function 1 over x squared blows up at x equals 0. And it's just a different type of continuity. It's called an infinite discontinuity. Okay. And A also, well, I want to say A would be a removable discontinuity, just like for part C. The discontinuity in A at x equals 2 is a removable discontinuity, just like you have in C, because for a, you could just add to the rule for the function that f of x will equal 3 when x equals 2. And then this function here would be defined for x not equal to 2. Okay, so in the homework, you're going to be asked about certain types of continuities. Is it an infinite discontinuity, a removable discontinuity? And you know, you only have, like, since there are only like a couple of choices, you only have one chance to get that kind of multiple choice question right. So the book goes into some detail in terms, like talking about continuous from the right, continuous from the left. They go into detail in terms of continuity, but I want to keep for now things simple. And I think intuitively you're going to be able to do the section 2.4 exercises on continuity with the discussion that we've had here. You might have to look at a few examples in the book. There's one on the intermediate value theorem, example 9. You'll need to look at that. But that example you'll be fine on that. So I want to try to give you some time in class to work on your new homework. But is everybody at least reasonably comfortable with continuity? Are there any questions on that? Sebastian's comfortable. Ian, excellent, excellent. Kelvin, John, excellent. Thank you, Rodrigo. I'm learning all names here. All right, well, let me stop the recording.